Greetings, geometry students. I sure hope a few of you find your way to the internet to get these notes copied after what I had to go through in order just to get the recording done. Had all kinds of computer and software trouble and all that. Oh, had a problem right there. There we go. Okay, so anyway, we're going to take a slight detour away from triangles and talk about just polygons in general. We're about to get into a different part of the discussion on triangles, and we need a little general information on how all polygons function and how they're named and things like that. So today's information is on Polygon Congruence. The date will be December 8th. Please copy down your objectives. Stated objective is to learn the definition for congruent polygons and discover the properties that accompany that definition. Now, congruent polygons is not a new topic for you. Probably spent a little bit of time in junior high working on them. Most of the information that you got there was good information. We're just going to add a few things to it. On your assignment, the student will demonstrate the ability to examine provided polygons and apply properties of polygon congruence in various ways. And your essential question for the day is, can I identify and name congruent polygons? As always, anytime you need more time to get something copied down, don't let the video just run past you. Press pause and then get copied down what you need, and then hit play when you're ready to move on. Okay, let's get started. Now, chances are from your discussions back in your junior high days, the term congruent was defined for you as same size, same shape. Well, we very quickly dispatched that at the beginning of the year and said congruent meant equal measurement. However, if you're going to talk about congruent polygons, the term congruent polygons, now you've got your same size, same shape. So the definition you got in junior high was a good one. It was just incomplete on its name. Okay. However, same size, same shape, we have learned this year in geometry that everything that happens in mathematics happens for a specific reason. Okay, so that means there must be something about the problem that causes two shapes to have the same size and causes two shapes to have the same shape. That's going to be a good bit of the focus of our discussion today, is to try to be focusing on that cause. Let's see if we can determine why two shapes have the same shape, why two shapes have the same size. Okay, and in fact there are two pieces of information that we are looking at. Obviously, we got two things that we're concerned about, one being the same size, one being the same shape. So two different things that we're focusing on. The first thing that we're looking at is our corresponding angles. Our corresponding angles will need to be congruent. If we can force our corresponding angles to be congruent, then this is the information that will actually cause two shapes to have the same shape. The second thing we are after is going to be our corresponding sides. We're also going to need our corresponding sides to be congruent. And if we can get that to happen, corresponding sides being congruent is what will cause us to have the same size of our two shapes. Okay? Now, both of those rules, both of those goals that we looked at right there kept using the word corresponding. Now, we have heard the word corresponding this year before when we were talking about parallel lines and more particularly transversals. Okay, as we're going to see, the word corresponding meant one thing for transversals. It's going to mean something different when it comes down to talking about polygons. Okay, so the clear piece of information right there is that we're going to have to be able to figure out what corresponds to what within our polygons that we are looking at. Okay, so let's see if I can't get you a new definition for the term corresponding. On the screen right now are a couple of triangles. And as you can see, we have all kinds of information marked on our two triangles. We've got all of the angle measurements and all of the side measurements in both of the figure on the left and on the figure on the right. These two triangles, by definition, are going to be congruent. And the reason is going to be because it fits the two-part definition that we saw just a moment ago. Okay, now back to that term corresponding. Corresponding basically means that there are locations from one figure to the other figure that share similar properties. Those properties might be side lengths. Okay, like this first bullet shows. For every side length on the left, there is a corresponding congruent side length on the right. Okay, so to break that down even further, if you look on the left side of the red triangle, there is a side length of 3. And if we look into the blue figure, we see also a side length of 3. In the red triangle, kind of on the top right there, we find a side length of 4. And if we look to the blue triangle, we find also a side length of 4, and they both have a side length of 5. Okay, so basically what we're saying here is that for each side length on the left, we find a matching value in the triangle on the right. That is part of the definition for being congruent. The other part of the definition for being congruent is that every angle measurement on the left, there is a corresponding congruent value on the right. And again, congruent or corresponding means they share similar properties. So in the case of an angle measurement, that would be degrees. So as you can see in the figure on the left, we have a 90-degree angle, and in the figure on the right, there is also a 90-degree angle. On the left, we have a 55, and on the right, we also have a 55, and so on. So these figures are, in fact, congruent because we have locations within the figures that share identical properties. Now, that was kind of a baby step problem. Okay, in the last example, it was very easy to see that the figures were going to be congruent since the figures were basically sitting in the same position. Okay, but the problems that we're going to run into at the high school level, many times your figures will not be sitting in the same position. That kind of disguises whether figures are appearing to be congruent or not. Okay, so here are the same two triangles, the same measurements, the same angle measurements, the same side lengths and all that. But as you can see, the one on the right has been rotated. Okay. Now, not doing anything tricky to you or anything like that, that first example, if we were to run into it on an assignment or a quiz or a test or something like that, it's more likely to look like this than it was that first diagram. But the question would be, are these triangles still congruent now that one is not positioned the same as the other? Well, the answer to that remains exactly the same as the answer was on the previous slide. For every side length from the red triangle on the left, there is a corresponding congruent value on the right. For every angle measurement on the left, there is there a corresponding congruent value on the right? And the answer to both of those questions is yes, there is. Okay, so it's not as simple as trying to just compare the left side of one figure to the left side of another, or the top side of a figure to the top side of another. That's not the way this works at all. So we're not looking for same positioning like we were when we were talking about transversals. We are looking for locations that have identical properties to them. Okay, now when identifying congruent polygons, as always, there is a particular way to name them. And the key to that is to name them according to which vertices correspond from one figure to the other figure. Okay. Now, back to the same two triangles that we have been talking about. You already have this graphic copied down, so don't copy down this picture again. You've already got it. Okay, but let's discuss it a little bit further. Please do copy down the statements here. If we are going to state that these triangles are congruent, we have to figure out which vertices are corresponding to which other vertices. Okay, now we've already gone through the protocol of establishing that yes, in fact, they are congruent. For every figure, every aspect, angle, and side length on the triangle from the left, we have a corresponding angle or side length on the right that are congruent. Okay, from one figure to the other. So they are congruent, but we may find it necessary in order to identify that fact, in order to answer a question, or possibly even to refer to it in the middle of a statement about a question. Okay, so let's take a look what corresponds to what. Now, we can say that vertex B corresponds to vertex Z, and it's pretty easy to understand why those correspond to each other. Obviously, they both have the 90-degree angle positioned near them, and they are both between the side lengths of 3 units and 4 units long. So plenty of evidence to prove to us that vertex B does correspond to vertex Z. Same argument can be used to explain to us that vertex A corresponds to vertex Y. Those are the vertices that have the 35-degree angle position near them, and they are the joining, those locations where the side length of 4 and the side length of 5 join together. So A definitely corresponds to Y. And similarly, C is going to correspond to vertex X. They've got the 55-degree angles positioned near them. They are the joining point between the side lengths of 3 units and 5 units. Okay, so C definitely corresponds to X. Okay, so establishing that information, we would be able to say, first off, remember when you identify our triangles, or any polygon for that fact, you state what kind of a polygon you have. In this case, we are saying triangles. So we're going to have triangle something is congruent to triangle something else. Okay, now we need to name the figures in the same order. So it does not matter which figure you start with. I'm starting with the red figure on the left, and I picked a vertex from the figure on the left, B. B got listed first in this little statement that we were making. So in the last half of the statement, we need to also list first the vertex that corresponds to B, which in this case is Z. So B gets listed first, so Z gets listed first, because they are corresponding locations in our triangle. Okay. So if we move along and pick on the A back on the figure on the left, we need to list what corresponds to vertex A in the second position on this statement, which would be vertex Y. Then vertex C and vertex X correspond to each other, and you've got your statement. Okay, triangle BAC is congruent to triangle ZYX. It does not matter which order you list the vertices in the first of the polygons that you list, which would be triangle BAC in our case, but once you have established the order by naming the first polygon, you must name the second one by exactly the same order. Okay, so another example. For the first time this year, we're going to see polygon bigger than 3 sides. Okay. And the term for polygons that have 4 sides is quadrilateral. We will actually spend a good bit of time talking about quadrilaterals later on in the year. And this example states that the following 2 quadrilaterals are, in fact, congruent. And then it tells us to name them. Well, it's a good thing that they told us that they were congruent, because we don't have enough information to decide that they are congruent on their own. We do not have the information regarding the angle measurements for these figures. Okay, so we do not know, wouldn't be able to tell ourselves that they are congruent, but the problem said so. The goal of this problem is for us to name these quadrilaterals, name these congruent polygons. Okay. Now, since we have 4 vertices for our quadrilateral, it would take 4 vertices in order to name it. Okay, and then we will establish that however we name the quadrilateral on the left, it's going to correspond to and be congruent to the 4 vertices from the figure on the right. But in order to name it, we have to figure out what corresponds to what in order to get the vertices in the proper order. Okay, this time we are dealing with quadrilaterals. We do not have any kind of a symbol or any kind of a cute little abbreviation or anything for quadrilaterals, so unfortunately we have to write that word out. Okay, so we're going to establish that we have a quadrilateral, which is then congruent to another quadrilateral, and then we will have to name our quadrilaterals respectively. Now, I already said it does not matter what order you name your first quadrilateral in, but you must name the second quadrilateral in precisely the same order based upon what is corresponding to what. Okay, so just pick a vertex from one of your quadrilaterals. I'll pick the E, just because it's closest to the front of the alphabet. Okay, vertex E from the figure on the left, and then I'm going to figure out what that corresponds to in the quadrilateral on the right. Okay. Well, one thing I notice about vertex E is that it is the joining point between the side length that has 1 tick mark and the side length that has 2 tick marks. So looking into the other figure, I want to find a location that has similar properties to that. And I see that there is a vertex that is joining 2 side lengths that have 1 tick mark and 2 tick marks, and that would be vertex L. So those two are corresponding. So we're going to start off with E and L for our 2 quadrilaterals. Now, it does not matter where you go next. Typically, you do move around the figure in either clockwise or counterclockwise motion, so we don't just start jumping all over the place as we name things. So I'll just move around clockwise from E to F. Okay, so now I need to figure out what corresponds to F in the right side quadrilateral. Okay, well, F is the joining point of the sides that have 2 tick marks and 3 tick marks, and if I look for similar properties on the right, I find that M is the location where the 2 tick marks and the 3 tick marks join together. And it shouldn't take too long to kind of establish the pattern. Okay, G, keep on traveling around clockwise around the figure on the left, and we should be able to keep traveling around the polygon on the right in order to continue naming it. But at any rate, G is between the 3 and the 4 tick marks, and on the right side between the 3 and the 4 tick marks is J. And then there should be only one vertex remaining in each case. It's H on the left. H is between the 4 tick marks and the 1 tick mark. Between the 4 and the 1 on the right side is K. Okay, so quadrilateral EFGH is congruent to quadrilateral LMJK, and once again, that the way you name the first one is not important. You can name them any order that you want, but once that order is established, you must follow the same order on the second polygon that you list. Okay. Now, one neat little thing about this is since we know that the vertices of 2 congruent polygons are listed in a specific order for a specific reason, we can tell what corresponds to what based simply upon the names of 2 congruent polygons without even really seeing the pictures. For example, a problem comes out and establishes for us that pentagon ABCDE is congruent to pentagon FGHIJ. Now, we haven't really talked about pentagons yet. Hopefully you know that pentagon is a 5-sided polygon. And even if you didn't know that, you'd probably be able to figure it out looking at the names of these polygons because they only have 5 vertices. 5 vertices means 5 sides. Okay. Now, everything that we really need to know about what corresponds to what from pentagon ABCDE to pentagon FGHIJ is established for us in the names of these polygons, because we know that the first vertex that is listed, A, would correspond to the first vertex listed, F. The same thing would be true for the side lengths. The first side length in pentagon ABCDE would be line segment AB. They are right there side by side. There's a line segment connecting those two vertices. Okay, so that would correspond to, on the right side, pentagon, or line segment FG, because those are listed first. Similarly, okay, an angle in the pentagon on the left, angle ABC. B would be the vertex of that angle because it was listed second. What does it correspond to in pentagon FGHIJ? Well, it would correspond to angle FGH. G would be listed second because that's the vertex. So the angle near vertex B and the angle near vertex G, they are corresponding and congruent based upon this statement. Okay, so what I'd like us to do is I have some questions here, and I want us to give these a try. Okay, so you are going to answer on your paper what corresponds to vertex C. Okay, so look at the pentagon ABCDE, and then look at pentagon FGHIJ, and ask yourself, in pentagon FGHIJ, what should correspond to vertex C based upon the positioning of vertex C in the name of pentagon ABCDE. Similarly, I would like you to answer what corresponds to line segment GH. So again, look at pentagon FGHIJ, look at the positioning of vertex G and vertex H, and then look at pentagon ABCDE and ask yourself which line segment is going to correspond to line segment GH. Also, what corresponds to angle ABC, what corresponds to line segment EA, and what corresponds to angle FJI. Answer those 5. Shouldn't take you any more than about 30 seconds or so. And the last thing you would need to do is to write your summary, jot down any questions you may have, and always keep your essential question in mind. Can I identify and name congruent polygons? I appreciate you finding the time to get your notes taken care of. We'll see you in class.